Hi. In this video, I will try to explain what this code is trying to do, what it was designed to do, and the basic parts of the moving parts inside the code that actually make it work the way it is designed to do, is designed to work. And also, in this video, I will explain several ideas that I thought of in the process of working on this project, and I haven't got a chance to actually make them part of the code yet, but I think that they are pretty simple to accomplish if it will be needed in the near future. So let's begin. This code is basically this code is a tool for, or a channel for creating a command control server and a command control client that are designed to connect to one another. The command control client, the client side of this code, is intended to be used to be deployed to the target system, to the victims system, and intended to be deployed as a scheduled task or some sort of a script that will run every once in a while, or at log on, at log off, something like that. And this will allow the attacker to update a certain file on the server side. That file will be generated on the first handshake between the client side and the server side. And once this file is updated with new commands that need to be run, the client side will pull that list of commands to be run and will run those commands and upload the results back to the command control server. The general idea is that the client side will use a DGA technique, domain generation algorithm, to find its server-side host. And the algorithm that it uses to create to generate the domain name is pretty simple. I'll show you in a minute. And that algorithm is basically based on the current date and time. And according to the current date and time, it will concatenate a few strings, a few words and prefixes and suffixes to create the actual domain name. And once it found that domain name, it will try to use it to find its host, or to find its server side. The idea behind that is that if the client will use such sort of a DGA algorithm, it will be much more difficult for the IT security team in the hacked organization, in the target organization, in the victims organization. It will make it virtually impossible or very, very difficult for them to find out that there is such a tool on the network that tries to go outside to pull lists of commands or to upload those commands responses. Because first of all, it will be a different domain name every day, and also that domain name will look like a very normal domain name. So because it will use real words that are concatenated together, it won't be sort of a gibberish domain name, and therefore it will be much harder to detect. Once the client side found the right domain name, or generated the right domain name, it will try to connect to the server via two ports. The first one will be a port that will be used for TCP communication, but it will look like, and I will explain later how it is done. It will look like normal HTTP connection, but it won't be connectionless, which is the normal way of HTTP, and that is important because it will use that connection to create an encryption key of an AES encryption key on both ends without exchanging anything in the transaction between them that can be used to infer the key that was generated. The way that it is done is by using the Diffie-Hellman algorithm for creating the same key on both ends without compromising its security or safety or secrecy between the two parties. The reason I chose to do that is because if I would have chosen, for example, something like TLS or HTTPS for connecting the client side and the server side, it might have been exposed, or it might have been this security of the HTTPS connection might have been compromised from the point of view of the attacker, of course, because many organizations use techniques for SSL offloading or SSL inspection and things like that, by using a proxy to access the internet, and that proxy will decrypt the traffic by using a certificate that is trusted by all the hosts on the organization's network, and therefore the data that I will send or receive as the C2 client on the machines that will be infected or that this tool will be deployed to, the traffic will be visual. It will be visible to the IT security guys on the that organization, and that, of course, is a bad thing for the attacker. So this is the reason why I chose to use HTTP, but instead to encrypt the data within the HTTP traffic. And to do that, I used the Diffie-Hellman algorithm to create the AES encryption key, the AES symmetric encryption key on both ends, both on the server side and the client side, and to use that key to encrypt the data that will be sent later by using normal HTTP requests to the server side. So this the preconditions and post-conditions of this attack tool. The preconditions for this attack tool, since this tool is not really an exploit, I mean, in the sense that it's not exploiting any vulnerability in a browser or operating system, etc. So, and it is just a rather simple client-server application that was written in Python. So it can run virtually on any computer, provided that this computer is running or is able to run Python version 3.5, and I make the implicit assumption that the penetration tool, the penetration process, will have to install Python version 3.5 if it's not yet installed, and install this client script as a scheduled task, or to integrate it somehow into another script that is already running, or as a start script or shutdown script, so something like that. The post conditions of this tool is that once it is running, it will be able to receive commands and upload the response from the client side. So this is the way to make sure that the installation was actually successful. And also, the tool is designed that way, that in such a way that it always will, the first command is actually hard coded, and it will try to run the command hostname as the first command that it will run. In the file readme.md, under the folder exploit in the project, I've written and explained all the things that I will talk about in this video, and also there's a paragraph of the instructions that should be used to run both the client side and the server side, and all the details about the communications and the ports that will be used, etc. So I think that this is pretty comprehensive information, so that you can use that to test that tool on your own computer, or in a VM or whatever. And also, I've listed in the last paragraph, I also have listed a few alternatives that came to mind. For example, I thought of using DNS tunneling for communication with a C2 server, but I decided not to do that because both, for several reasons. One of them is that TCP DNS queries will stand out, will be easily detected, because most DNS queries are obviously UDP, while TCP DNS requests are usually for zone transfer. So I thought that it would be easily detected by SIEM solutions or EDR solutions, etc. So I decided not to do that. And since that UDP DNS queries are limited in size and might not be able to convey all the outputs of the commands that I would like to run, and send them over to the C2 server, and also because it's not very reliable in communications that go outside of the organization to the internet. So this is why I decided not to use DNS tunneling. Another option was to use a cloud storage, for example, to decide to use a Google Drive, OneDrive, Dropbox, something like that, to store the commands in one folder and store the results in a different folder. So the client side would just have to use the API of Google Drive to connect and pull the list of commands and execute the commands and upload the responses as files in the other folder. I decided not to do that because of two reasons. One was the fact that in my experience, many organizations, especially financial organizations, would normally block the access altogether to cloud storage because of these, because of that reason, that someone might use it for that purpose, and also to prevent data leakage. That, for example, an employee will copy data of the company to his own Google Drive, etc. So this is why I decided not to do that, and also because if that organizations using something that would prevent access to cloud storage, this mechanism will fail completely and won't be able to do its job altogether. And in the solution that I chose, it will send the data or receive the commands, even if the communication is couldn't be encrypted properly, and I will get to that in a minute. And also, there are things that I thought that can be done to improve this tool, and I have listed them over here in this paragraph, in the last paragraph of the readme.md. So you might want to take a look and see those ideas after we are done. After I'm done explaining the MO of this tool. So let's begin with the client. The client side is a Python script, script, yes, with a single class called main, and the first thing that would run on this from this class would be the method called run on the main object that was created of this class, and the run method does the first thing that this method would do is it will use the method called getDhSessionKey. This is actually the way that the client would connect to the server and use the Diffie-Hellman protocol over TCP connection, but will send messages and receive responses that look very similar to HTTP. So this is intended to be used to deceive deep inspection tools or protocol analysis tools that will think that they are actually looking at an HTTP session, but and won't be able to tell that this is in fact a normal TCP connection and have absolutely nothing to do with HTTP. And in this session, the two parties, the client side and the server side, will exchange information, non-confidential information. That this information cannot be used to infer the actual key that will be generated on both ends. To explain that even a little bit deeper, this is actually the method that I'm talking about. It will use a class called Diffie-Hellman from the library, from the Python package called Diffie-Hellman Diffie-Hellman, and yeah, and this and it will use that, and it will instruct it to create a key of 32 bits, 32 bytes, which is actually 256 bits, which is the longest possible AES encryption key possible, if I remember correctly. And then it will use this tool to generate a public key, which is actually a number that will be later exchanged between the two parties in a certain way, and that information will allow both parties to create the same key while still not exposing anything that can be used to infer that key to a third party that will try to sniff the traffic, etc., and try to get it from there. So so the first thing is that this method would do is to use the getNodeDGA URL base, because this method would use the simple DGA algorithm that I mentioned to figure out what URL to use. And well, in this tool, since I didn't want to actually create domains for the purpose of this demo, I decided not to use this DGA algorithm over here in this function. I'll get to that later, and I just used hard-coded the home address instead. So once the Diffie-Hellman session key, Diffie-Hellman session key method figured out which host name to use and which destination port to use, it will create a random path which will just be used to as part of fake URL that will be sent to the server. I'm just reminding you that this is not an HTTP connection. It just should look like an HTTP connection. So I'm trying to create it and to make it look like a real HTTP connection, and to make it look like a random HTTP connection, so it won't be it won't be possible to block access to that URL or any parts of it by using fixed information. So the intention is not to make it possible or to make it very, very hard to create a signature that will be used to block that tool from connecting to its server side. So I'm creating a fake user agent, and then I'm encoding the Diffie-Hellman public key as a base64 encoding, and we create sort of a connectionful or a not connectionless HTTP request, and that would look something like that. It will create a GET with a URL that actually means almost nothing, because the only thing that is meaningful is the client ID. This client ID is actually an ID that it is just generated every time the client is starting in the init method or in the constructor method of the class as a GUID. So so it will send that as part of the URL, and also as part of and it will send the user agent and the normal header of normal HTTP requests, and it will use a key as a cookie, a fake cookie, which its name will be the client ID, and its value would be the base64 encoding of the Diffie-Hellman public key. It will create a socket, and then it will connect, and then it will send all the HTTP requests. And it will receive only the 4096 bytes and try to parse the data. And the data would be actually something that looks like an HTTP response, and it will contain and the most important part, it will contain a few lines of information, but as you can see, those variables are actually not used. So the only thing that is actually meaningful is the server Diffie-Hellman public key, which is also encoded in base64, and therefore it will be decoded in this on this end. And the public key, the decoded public key, will be used as an input to the Diffie-Hellman method called generate shared secret, which in short, it will use an algorithm based on modulus and several other, basically on modulus as an irreversible mathematical function that will be used to create the encryption key in such a way that it cannot be inferred by anyone else, and that encryption key will be returned from the function, and also, won't be returned from the function. It will be stored as a variable on the class itself, on the main class. And it will be the thing that I'm using here is just to cut it to 32 bytes, just in case that for some reason it's not. It's actually not necessary, and probably can be just deleted. And yeah, so now we might have a session key, and if for some reason this process was unsuccessful because, for example, someone blocked the access to that port of the TCP connection, or for any reason at all that this process was unsuccessful, then the session key will be set to none. This will allow the other two methods, the other method to use. It will allow the other step of the communication to use unencrypted channel and get the information and be able to send it back all the same, even though it is not encrypted. Because for the attacker, the encryption is not so important because it's not really. I mean, it's not that important for the attacker to keep the information of the client safe. So the next step would be to use the method called get command to run, and get command to run will basically also use the client ID and create a random GUID that will be converted to a string without the dashes to make it look more like a number, or more like a sequence of letters and numbers, which is practically meaningless, but it will make it harder to detect on the communication by using, for example, deep inspection tools and etc. and tools of like that. So if the session key is not null, it will try to encrypt the data by using AES. Therefore, it will encrypt the session. It will use the session key as a key for the encryption, and will encrypt random data. And actually, this encryption is not very crucial, or even not very important to the successful success delivery of the information back and forth. But it will just make it look more normal, more like a normal traffic, and less as something that can be detected that it is a GUID. And for example, certain types of GUID have the same have an indication of the version of the algorithm that used to create them. But if I encrypt it, then all this information is just meaningless completely. So I'm using the famous Python package called Mechanical Soup. This is a package for imitating a browser in the code of Python, so that you can maintain session, etc. But for this tool, I'm actually using it to do a very simple task, which probably could have been done by using even simpler libraries like URL-lib and similar other libraries. But I just used that because this is the first thing that I thought of. I have no better explanation for that. So I create a URI, and this time it is important that important to note that this URL is actually a real URL, and it will be used to connect to the server via real HTTP connection, which is connectionless HTTP, like it should be. So this is why I named it the real HTTP server. So and also it will use the it will connect to the server side, and will send the client ID as part of the URL. And what it will get as a result is actually a cookie which has information, encrypted information, encrypted and encoded information that includes the command that needs to run, the latest command that has been added to the file on the server side. So it will try to decrypt that data by using the AES encryption, the AES decryptor, and that AES decryptor will use the session key that we talked about. Sorry about that. That we talked about earlier. And then it will use the session key and then decrypts the information after decoding the base64. We have to use base64 here because it is using HTTP, and HTTP does not support the upload or the download of binary information, so it has to be encoded. Usually this is the way it works in HTTP, that it is using base64 to do that, but there are other types of encoding that's sometimes used, but I chose to use base64 because it is the most commonly used and the most popular, I think. At least the way at least to the best of my knowledge, anyway. So, and if the decryption fails, it will try to use a simple base64 decoding, because if the encryption fails, it assumes that if the decryption fails, it also assumes that the encryption failed as well, so the data is actually not encoded. So that will return the command that needs to run. And if it finds a command that needs to run, it will simply execute that command. The information is not actually a command like ifconfig or something like that. It is actually a JSON that includes several information about the command, for example, the arguments, and several other details about the command that needs to be run. And then it will load that JSON into this object, and will use it to create both a command and a list of arguments if they are actually included in the JSON object, and then it will run it by using the subprocess class of Python, and will use the shell interaction so that even commands that need shell interaction will work the way they are supposed to, and all the output will be decoded and returned to the caller, in this case this variable, and then it will use another method called report command status, and the report command status will also use the client ID, which is the same client ID. The client ID is generated once the class is loaded, so as long as this tool is still running, it will always have the same client ID. And one of the ideas that I thought of that should be used to improve that tool is to save that client ID, for example, in some place on the registry or in a file somewhere, so that it will the client will be able to use the same client ID in every request, even if the client was even if the computer has shut down since the last time this client ran, or even that the client script is ended and then it has run again, for example, as a scheduled task. If it, in the current situation, in the current state, if the client script is deployed as a scheduled task, it will have a different client ID in every time the task is run. This is not the best thing to do, but this is what I could do in the time that I had. I think that it is not so it's not so difficult to implement it in a way that this tool would be able to keep that data in a registry or in a file somewhere. It's not very difficult to do. So Um, that again, it will create a random number, which is essentially a GUID. By replacing the dashes with nothing, it will just create a random set of letters and numbers, and then it will hash it will create a hash by using the SHA-256 algorithm to hash the command that was run, and encode the result of the command as a base64 encoding. And then also, again, like before, if the session key has been selected, it will try to use it to encrypt that data before sending it over to the server. And if that encryption fails for some reason, it will just encode the data as a base64 and with no encryption at all. So then quite simply, it will use the mechanical soup browser, create a random number. The random number will be used both as part of the URL over here, and as a query ID, as a variable that is included in the query arguments in the GET request, and that variable will have that argument will be set to the hash of the command, and in the cookies it will create a cookie named after the client ID, and after the client ID, and the value would be actually the base64 encoding of the result of that command. I didn't see the need to encrypt that data, but it might be at the time, because I thought that detection tools will tend to use detection of commands like ifconfig or something like that, because it's much more predictable, but the output of the commands is sometimes less predictable. So I decided not to encrypt that, but it might be a good initiative to decide to encrypt that as well. So maybe that can be done later. So that's it. It will just create a post request of the URL, and it will send the cookies in the cookie jar over here, and the server will store the details of the result of that command in a file, so that the attacker will be able to find it and see the results. So we're actually done with the client side. So now I'll head over to the server side, which is even much more simple, I think. So the server side also contains a class called main, and that class also has a method called run. So let's examine it. Yeah. So the run method will get as a parameter the host on which the server side should listen. Normally it should be 0.0.0.0, which is essentially means that it will listen on all the IP addresses that are assigned to this host of the C2 server. And the second argument would be the battle port and the TCP port. The battle port is actually the port that will be used to serve HTTP requests by using the Bottle framework. If you are not familiar with the Bottle framework, it's actually kind of like Flask, if you are familiar with that. It's a simple framework that, or actually a micro framework that allows the programmer to develop applications that respond to HTTP requests of various different types of HTTP requests. So I'm using this framework to provide that ability to the server side, and also the TCP port that will be used, as I mentioned earlier, to exchange the data that will be used to create or to generate the symmetric AES 256-bit key on both ends without exposing the data that can that can be used to infer the actual key used. So in order to do that, I'm actually using a different thread to host the TCP port, and a different thread, which actually is the main thread of the application, to host the bottle framework application that will respond to HTTP requests. Internally, the bottle framework actually using different threads, but this this method will actually run until killed to host the HTTP server side. So the methods on this class actually are divided to different types. Methods that have, for example, the @ sign, the decoration above them. For example, this one, it means that it will respond only to HTTP POST requests of URL that matches this regular expression, and the things in those brackets will be used as parameters, or actually arguments for this method. So the data that is inside between these two forward slashes will be sent to here, etc., and so forth and so forth. So so as you probably remember, the first thing that this and then, sorry about that. The other type of methods is methods that the other type of methods is methods that don't have this decoration, like this one, that don't have that decoration above them. Like, for example, this method, or this method, etc. Those methods or this one, those methods won't respond to HTTP connection. So if you remember the run method, we said that it will actually run this method as the method of the thread. This thread will be used to listen for TCP requests that will be used to get the AES key by using the Diffie-Hellman algorithm. So this method actually, what it will do is it will create a socket, bind to a TCP port and the host, and will listen for a maximum of 50 concurrent requests, because I didn't want this server to be overloaded, obviously. So I limited that to 50 requests by using a hard-coded number. Also, again, I think that the better way of developing it would be to store that in that information of the 50 connections as a configuration file of some sort, something that I can tweak later. But for the purpose of simplicity of the of this demo, I decided to use it hard-coded. So the thing that it will do is, well, it creates an endless loop. This endless loop will accept connections, and once a connection has been accepted, it will send that information about the connection, about the request, to this method, and it will send it the client socket and the address number, or the IP address number. So this is actually the method that will handle the TCP connection, the TCP requests for a Diffie-Hellman public key, so that it will be used later to create the AES encryption key, AES symmetric encryption key. So it will read from the buffer 4096 byte, and then it will decode the string to a string, the data that it has read to a string, and then it will try to parse that string and get that important information from it. As you can probably remember, this information looks like an HTTP, but it's actually not an HTTP request. And the most important part in that information is actually the cookie name, which is the client ID, the unique GUID that has been selected as the client key, and the cookie value, which has the actual Diffie-Hellman public key of the client side. So it creates two variables to store that information, and then it uses the Diffie-Hellman class from the Diffie-Hellman package, like I showed earlier, and it will generate a public key, and that public key will be used. That public key will be used later to send it to the client. I'll show it in a minute. And the client-side public key is being used by this method to generate the AES key on the server side, and it will create a file in a specific path. I'll show the path later, and it will create a key file, which is essentially a JSON file, which includes the client IP address, the client ID, the Diffie-Hellman key, and the session key that will be used to encrypt the data, and also the server Diffie-Hellman public key mainly for I think that the best way to describe it will be mainly for debugging purposes, or yeah, I think that's pretty accurate. So it will open that file, write that JSON to it, and close the file, and then it will send the client something that would look like an HTTP response. You see, HTTP 1.0 200 OK, the HTTP status, the HTTP status name, the date, the current date in the right format, and it will declare an HTTP server, which is Microsoft IIS 6.0, which probably doesn't exist in any company now, which is actually, if I remember correctly, it was used. No, I think that it was used in Windows 2000 and only. Anyway, so it will declare the content type and will set a cookie. The cookie will actually, the cookie name will be the client ID, and its value would be the server-side public key. This public key will be used on the client side to also generate the HTTP, the AES symmetric encryption key. Then it will send a dummy HTML body of, for example, Nginx, just to make it look even more like a normal HTTP request, and it will send all that data to the client and will close the connection. But in case there is an exception for some reason, it will send an HTTP 404 page, because that will make it even in such cases that it had failed. I thought that it would be important to send the client side data that will make it look like a normal 404 page, so that because we can overcome that issue by using non-encrypted channel, it is important to keep the connection as still as possible and to avoid detection. So this is the reason why, even in an exception case, I chose to send a 404 page to the client. And then it will just close the socket and the data will be sent. So at that point, we should have, but not necessarily have, an encryption key on both ends. So once, if you remember from the previous part of the client, the second part that the client side would do is to connect. It will connect to the get command method by using normal HTTP, as you can see now by using that I'm using the @get declaration of bottle. That means that it will be it will use that URL of a random data, then a client ID, and that information will be sent to that function, to that method, and then it will use that information to find the file on the client, on the server side. And if such file exists, it will actually tail it and use the last command entered in that file and will send the JSON of that command to the client. I'll explain in a bit how this is done. But if that information is not, if that file is not actually exist, that means that this is then the first time that this client ID finds that server. So in that case, it will simply use that command to send it to the client, and that is what I mentioned earlier, that the default command that will be sent as the first command to every client would be the hostname command. In such a case, it will simply write that command to the file, and we'll use that command later to send that to the client. So the next thing that this method get command would do is to try and encrypt that data by using the session key that we discussed, that was generated in the TCP connection, and then it will read the file of the encryption key and will load that JSON, and then it will create an encryptor, which is actually based on the AES based on the AES encryption package of Python, and it will use that to use the session key and then to encrypt the command that needs to be run, the JSON that includes the command that needs to be run. And if for some reason the encryption failed, it will just encode it by using base64, and then it will create a cookie and send that information, which is either the base64 encoding of the command or base64 of the encrypted command, depending whether the encryption was successful or not. And then it will replace the header of server to the same header that we used in the TCP connection, so that to confuse any deep inspection tools that exist in the network. So to fool them to think that it is actually the same server that is answering on two different ports, and then it will just simply create a dummy HTTP page of, like I said, Nginx, and that will be used, that will be sent to the client, which will ignore all this data and will just use the cookie to extract the JSON of the command that needs to be run, and will run it and then upload the response. And the response will be uploaded by using the HTTP post method to this URL, which is essentially a random path / a client ID / the hash of the command. So In that case, it will, if that request is being received by the server, by the bottle server, then um, it will get the command hash. And if you remember correctly, the command hash is being sent as request as a get argument, which the argument name itself is random, and the argument name itself is being sent here, so that this line will use this random value to find the right variable on the get request, and that variable should be set to the command hash, and it will store it over here, and the result of the command should be pulled out or decoded from the cookies value, and that will be stored here, and then it will try to decrypt it, to decrypt the command hash like this over here, and if the decryption fails, it will just assume that it is actually the command hash is the command hash that was sent, and then it will get several informations like the remote address, which is the remote IP address of the client, and I'm fully aware of the fact that the client IP is most likely in most organizations is in fact the public key of the organization, because in most organizations users don't get a public IP. So this is why I chose to save to that file both the client IP and the client ID and the command hash and the result base64, and that will allow the if, for example, the client ID will be saved like I proposed earlier, that will allow the attacker to actually know how many computers and which computers, or not which computers, but how many computers inside an organization have been already infected, because if they have the same client IP, sorry, that means that they are all behind the same not behind the same public internet IP. And if they have multiple client IDs, and the client ID is saved on the client, which is not the case right now, but I think that it is the wise thing to do, which is pretty easy to do, and then the attacker could know how many computers are behind the same IP, which essentially means that they are in the same organization. And if he has the public IP, that is not very difficult to find out in which on which organization we are talking about in most cases. So then it will create a file, write all this data to that file and close it, and also in the response we will replace the server header like I explained earlier, and send a bogus HTTP body. That pretty much sums everything. I think we have touched all the methods on this class but one. This is a very simple method, which is essentially means that if, for example, this server is being addressed or has been sent a request, which is any request, I mean post, get, whatever, and that request has resulted 404 status, because, for example, if someone tries to connect to that server by using a different URL other than the ones listed here, Bottle will respond with 404 response, normal 404 response, and I decided to overload it so that it will use my response of 404, because that way I can both replace the server header so that it will still look like a normal HTTP server, and also to avoid sending any body in that response, so that it won't reveal anything about the behavior of the server. So this is pretty simple and straightforward method. And the other thing that I wanted to include in this video is just the constants that I'm using for saving all this data. I mean, the path that I'm using will be /TMP/C2 server, and if any of, and then those three directories underneath that path, which essentially means this directory will be used to create files that contain all the list of commands that the client side should run. These files contains this directory contains files that contain the keys, that the AES keys that each client would use, and also this path contains the reports of the commands that were successfully run by the clients, and those reports will stay there for further investigation of, I mean, if the attacker wants to see the results of the commands of specific computers, he can look in the files that are stored under that directory. And to make sure that all those paths actually exist in the constructor of this class, I'm making sure that all of those directory actually exist. Yeah, the only thing that I can think of now is that if, for example, it couldn't create a single directory, it won't continue to trying and create the other directory. I think that the odds for that are pretty slim, because it will either have the root path, or it won't have the root path, because in some cases, for example, what I did on my computer was that I used the TMP directory, which is being wiped out in every restart of my computer. So it is either there or not there, but it will never have an option, or it will never probably it will never fail in creating a certain directory, but it will always fail on creating all of them or none of them. So this is basically the entire explanation of how that works. Yeah, I think that the only thing that I will do next would be I will create another video of the actual demo, so that you can see how that actually works. So thank you very much, and I hope that this was informational and enlightening for you. And feel free to send me any questions if you have any. Thank you very much.